reverse engineering / modifying an electric leaf blower's DC power circuit. So we have assumed values on the schematic. They're not proven as correct, but we can start with the actual DC amperage draw we need at the leaf blower by dividing the effective watts into the total voltage going into the leaf blower, and then we get an idea of the given battery. So that's a 20 cell series wired DC voltage battery at 3.6 volts per cell. So it is a 72 volt battery, lithium ion, or a lithium polymer battery. So we have a max current amp output at 30 C discharge as specified on the battery times 7.5 amp hours, so 150 amps DC. And so we need to only calculate current needed, and that is going from positive to negative as DC electricity flows from positive to negative. So the total current discharge or discharges from the positive terminal is equal to the total current. So we're only tapping a specific amount of current from the battery based on the circuit design. So if we tap at the parallel junction, the total current across the parallel values of the blower's resistance and the battery charge LED lamp, we come to 22.7. And again, this is subject to correction, so we have to do a little bit of troubleshooting. So current remains constant on series pathways. So identify the current at 22.7 amps discharging from the positive terminal. Then we access Ohm's law. For DC circuits, voltage is equal to current, amps times resistance, ohms. So then we can solve for resistance. So that's voltage divided by current. So we'll just divide the voltage drops on series into the assumed ampere rating for the given series components, the temp sensor, speed controller, and low voltage cutoff circuit. So then we can populate the theoretical ohms values for the series circuit, but we still have to test and see if this is simply reverse engineering or an actual mod. So then the fourth parallel resistor, we solve for its resistance by dividing the voltage, the constant voltage across the series circuit, the blower, and the battery charge LED. And we get 60 volts into 1 amp, so 60 amps. So the next step is to modify the resistor values based on the constant current flowing from the positive terminal down series. So we have our on-off switch at the trigger. So thereafter, we can do the test checks. And this is where it will probably need to be modified. So we have to consider the ohm load for the second parallel circuit as the internal resistance or load resistance of the blower, so we can divide the 60 volts into the ampere rating of the blower. So we get 2.77 ohms. So then we have to complete the second parallel circuit by putting a bridge across here. Now it is actually a functional parallel circuit, so the current at the load can be tested, and it is 21.7, so that's good. Next, we have to combine these two parallel resistors, 60 ohms and 2.77 ohms, using the inverse sum law of combining parallel resistors. So upon doing so, we calculate a required combined parallel resistance at the end of the series junction of 2.76 ohms. So if we were to divide the constant voltage across parallel to the blower into the combined parallel resistance, we need then a value equal to 21.7 amps plus the 1 amp battery charger LED lamp. So this comes to 22.7. However, when we do the combinations, we have to then validate the actual combined resistance. It's 2.64 ohms at the end of the series pathway to parallel. So we need a combined parallel resistance of 2.64 ohms instead of 2.76 ohms. So we'll rewrite that in there. So then if we solve for the fourth resistor, we'll cross out the 60 ohms right here, and then we'll solve for the fourth resistor. We'll let the R4 equal to X, so it's easier to solve. So if we use the inverse algebraic method, we can just do it compartmentalized in a compartmentalized manner. So 1 over 2.64, get 0.379, subtracted from 0.361, so we get 0.018, find its inverse, and then we get a value of 55.6 ohms. So we have to then test that and see if that's true. If we combine these two resistors in parallel, we do get 2.64 ohms parallel combined resistance. So we'll just write that in there, 55.6 ohms. So the current across the first battery charge LED lamp is validated at 1.08 amps. So we rounded up to 1.1. And we modify the battery charge LED to 1.1 amps. And then we add the two current drops on parallel together, and we get 22.8 amps. So we need to go up by 1/10 of an amp on all of the devices on series. And then we can retest this again, and they all come to the approximate value that we need. So then we can take the constant current of 22.8 amps flowing to parallel, and then the current will split, then drawing 1.1 amps to the battery charge LED. That's the light that tells you how much battery storage is left, and then we subtract another 21.7, and then we go to 0, so that's correct there. So now we got to compute all the voltage drops and see if we have the right battery, and we come to 77.5 volts, but we only have 72 volts available, so we need 5.5 volts more DC voltage. So we'd need a 77.5 volt battery, but lithium polymer batteries only come in increments of 3.6 volts DC per cell. So we need to round up to 22 cells lithium ion battery. So look for that one. And so the actual voltage is 79.2 volts DC. And so we add in 2 more cells. So that's just a battery replacement, but we don't change the 75 milliamp 7500 milliamp capacity. We keep that in the battery specs, and we just change it to 22 cells. So now we can identify the battery voltage at 79.2 volts DC, the total circuit voltage at 77.5 volts DC, total current draw at 22.8 amps. And then we do a last check by using Ohm's law for total voltage on DC circuit. So total current times the total resistance. So we combine the parallel resistors once again and add it to the sum of the series resistors. So 0.22 ohms plus 0.33 ohms plus 22 ohms plus 2.64 ohms, and we get 3.141 ohms total resistance. So when we add multiply these out, we get 77.7, so that is 99.74% accuracy. So that's validated as correct. That includes a rounding error, so that's correct. And then the total circuit voltage is between 77.5 to 77.5, 77.7 actually, but so 77.7 will actually discharge, so that's good. So we come within the rounding error of 3.41 ohms total circuit resistance. So all calculations and reverse engineering mods are validated as correct. So we'll finalize this here. So then if the parts are not available or data are not available, you can go ahead and do the correct modifications to put equipment back into service, especially if imports are not available. Thank you for watching this lecture and have a great day.